The variance of a random variable. First, let's review the variance of an entire population of values. Um, for example, we have an entire population of values as below. That is x1, x2, x3, and go on until xn. We have an entire population of values here. The variance of this entire population is this one square equals 1 over n sigma I equals 1 to n. Here is xi minus mu bracket square. So this formula is to calculate the variance of this entire population of values. In here, the mu is the mean of the entire population of values. So mu equals 1 over n sigma I equals 1 to n. Here is xi. So this is mu. The variance of an entire population, this one has another form. It can be like this. This formula has another form. This equals 1 over n sigma I equals 1 to n. And here is xi square minus mu square. This is another form of the formula. They are in fact the same. Here, if we open the sigma, so we can get 1 over n bracket x1 square plus x2 square plus until plus xn square. Here minus mu square. Now I will describe how to go from the top, from this formula to the bottom formula. So 1 over n sigma I equals bracket xi minus mu square. So this equals 1 over n sigma I equals 1 to n. Now we calculate this square. So this equals xi square minus 2 multiply mu multiply xi plus mu square. Now we can remove the brackets. So this equals 1 over n sigma I equals 1 xi square minus 1 over n sigma I equals 1 to n. Here is 2 multiply mu multiply xi plus 1 over n sigma I equals 1 to n mu square. Let's go ahead. So here we still copy this term. Sigma I equals 1 to n. xi square. Then minus. We can move 2 multiply mu left. So this is 2 mu multiply 1 over n sigma I equals 1 to n xi plus n 1 sigma I equals 1 to n mu square. Let's go ahead. So let's look at here. From this equation, we can get sigma I equals 1 to n xi equals n multiply mu. So here, we still copy 1 over n sigma I equals 1 to n xi square minus 2 mu multiply 1 over n multiply. So let's look at this term. We use n multiply mu to replace this term. So plus 1 over n multiply. So this guy equals n multiply mu square. So here is n multiply mu square. So let's look at here. So we can cancel this n and this n. Cancel this n and this n. So let's go ahead. So here should equal 1 over n sigma I equals 1 to n xi square minus 2 mu square plus mu square. So at last we get equals 1 over n sigma I equals 1 to n xi square minus mu square. So this term equals this term. The variance of the population describe the spread of the population. The larger the variance, the more spread out the numbers are from the mean. For example, let's look at the following two entire population of numbers. The first population is 1, 2, 3, 4, 5. The second population is 1.5, 2.5, 3, and 3.5, 4. The variance of the first population is larger than the variance of the second population. The reason is that the numbers of the first population spread out more from the mean than the numbers of the second population. Now let's go back to look at the variance of a random variable. For example, we have a random variable y. If we measure y an infinite number of times, we would get an infinite number of results. For example, maybe the results are y10, yn minus y2, y30, y5, and so on. It's countless. It's countless. There are countless results. The variance of the entire population of these countless numbers is just the variance of the random variable y. Now we use the formula. This equals 1 over n bracket x1 square plus x2 square plus xn square minus mu square. So we use the formula to calculate the variance of an entire population. We use this formula to calculate the variance of this entire group of numbers. First, let's find the mu of this entire group. We know mu is the mean of this entire group. And from the video about the expectation of a random variable, we know the expectation of the random variable y is just the mean of these countless numbers. So the expectation of the random variable y is just mu. So this equals mu. So let's go ahead. Now we use this formula to calculate. So this equals here, because this entire group has countless number of values. So we use this infinity to represent the count of this entire group. So we use this infinite symbol to replace n. So here is 1. And now we use the actual values of this entire group to replace the x1, x2, until xn. So here is y10 square plus y10 minus 2 square plus y30 square, and go on, countless. And minus, here we use the expectation of the random variable to replace the mu. So here is the expectation of y square. Let's go ahead. This equals infinite 1. Now let's look at the guys in this bracket. There are countless terms in this bracket. And in these terms, there are countless y1 square. There are countless y2 square. So the number of y1 square is just the probability that the random variable equals y1 multiply the count of the entire group. The count of the entire group is infinity. And the number of y2 square is just the probability that the random variable equals y2 multiply the count of of these infinity numbers. The count of them, we use the infinity to represent, and so on. The count of yn square is just the probability that y equals yn multiply the count of the infinity numbers. We use the infinity to represent it. So now let's go back to here. So here, the bracket. So these terms can be read as y1 square multiply the probability that y equals y1 multiply infinity plus y2 square multiply the probability that y equals y2 multiply infinity, and so on. Go ahead until plus yn square multiply the probability that y equals yn multiply infinity bracket minus the expectation of y square. This equals. Now we can move this infinity out of the bracket. So this equals infinity over infinity. Here, y1 square multiply probability that y equals y1 plus y2 square multiply probability that y equals y2 plus go on plus yn square multiply probability that y equals yn bracket minus the expectation of y square. Now the top and bottom can be cancelled. Now this part can be written as this equals sigma I equals 1 to n. Then here is yi square multiply probability that y equals yi minus the expectation of y square. So we get here. So this is just the variance of the entire population of these countless numbers. This is just the variance of the random variable y. So now let's go ahead. We use var y to replace this guy, and we use expectation y square to replace this part. Now we get var y. This represents the variance of the random variable y. This equals e expectation y square minus expectation of y square. Normally this is called the mean of the square minus the square of the mean. So that is the mean of the square minus the square of the mean. The square of the mean. So this formula shows how to calculate the variance of a random variable. Now let's go back to the median. The median of a random variable. We know that if we can find a smallest possible value n that fulfill this inequality, the probability that the random variable x less than or equal to n, this is larger than 1 over 2. If we can find a smallest possible value n that fulfill this inequality, then m is the median of the random variable. If we can find a smallest possible value n that fulfill this equation, this equals 1 over 2, then the median of the random variable x is the mean of n and the next largest possible value. So this part is to calculate the median of a random variable. Let's imagine if we measure the random variable an infinite number of times, we will get an infinite number of results. Maybe the results are x minus 2, x2, x10, and so on. There are countless of them. If we arrange the countless results from the smallest to the largest, we will get x1, countless x1, then x2, countless x2, and so on, until we get xn, countless xn. And we use these two formulas. We just find the middle number of this entire population of countless numbers. So all the formula to calculate the variance, the median, the mean of a random variable are derived from those formulas to calculate the variance, the median, the mean of an entire population of values.